Welcome, everyone. Today, we're diving into a fascinating topic, optimizing deep research agents. Specifically, we'll be looking at how we can find simplicity on the other side of complexity when it comes to reinforcement learning, or RL, training. Let's get started. Let's start by looking at where the industry is right now. The current state of RL in deep research is, frankly, pretty fragmented. These deep research agents typically operate through multi-round retrieval and decision-oriented generation. Now, while RL feels like a perfect fit for this kind of long-horizon paradigm, the actual training recipes people use today are just a messy collection of varied configurations. As a result, engineers are struggling to identify which factors actually drive real performance gains. To solve this, we need to deconstruct the training pipeline. To systematically assess RL's true role, we need to isolate the impact of different settings within a controlled environment. Using the Search R1 architecture via Qwen 2.5, we're going to focus on three main dimensions: the prompt template, the reward function, and policy optimization. Let's dive into our first major insight: more reasoning does not equal better performance. There's a common myth out there that extended reasoning chains are always beneficial. However, the reality is quite different. The data shows a clear negative correlation. As explicit reasoning and retrieved information increase, accuracy actually goes down in deep research settings. Unchecked reasoning expansion heavily degrades outcomes. This brings us to the danger of the widely adopted slow thinking template. This template forces a think tag before every single action. What happens is it introduces an optimization bias. The policy learns to stack these tags just to maximize sparse rewards, eventually triggering uncontrolled reasoning growth and a complete training collapse. The agent falls into a self-reinforcing loop of outputting empty think tags. This is exactly why a fast-thinking template is needed to directly limit this. Our second insight tackles the reward metric. It turns out that F1 supervision fails when it comes to intermediate constraints. Many believe that F1 scores are the superior reward metric for training. But in reality, F1-based training exhibits significantly higher instability compared to strict exact match, or EM, rewards. While F1 produces longer sequences, it actually results in lower overall multi-hop accuracy, scoring 0.391 compared to EM's 0.422. Let's look at the anatomy of this training collapse, which we call answer avoidance. Why exactly does F1 fail here? Because sole outcome-based supervision lacks constraints on the intermediate decision-making process. Think about it: if missing an answer gets the exact same zero reward as giving an incorrect one, the model degenerates into a lazy local optimum. It simply refuses to answer to avoid the effort of complex reasoning. We literally see the answer rate plunge as the model avoids the question entirely. So, how do we fix this? We revitalize it by creating F1+. We augment the standard F1 reward with lightweight action-level penalties. We basically subtract a penalty for 0 searches, and a penalty for 0 answers. This eliminates the refusal behavior because it explicitly forces active participation. By stabilizing the training dynamics, F1+ ultimately allows the model to surpass the EM baseline. Now for insight number 3, newer algorithms aren't always better. The old consensus assumes that modern algorithms like PPO or GRPO are the definitive state-of-the-art for reasoning agents. But the reality? When evaluated strictly on stability, final accuracy, and reasoning cost, the classic, simpler algorithm wins out. That's right, the classic reinforce algorithm outperforms both PPO and GRPO. We found that GRPO exhibits the poorest stability and collapses frequently. PPO is stable, but it stubbornly maintains a high, rigid search count, failing to adapt to simpler queries. Reinforce, on the other hand, achieves the highest overall accuracy with the lowest reasoning cost. It learns a highly compact strategy, averaging just 1.35 searches compared to PPO's 1.97. Why does reinforce work so well? It avoids baseline interference. The auxiliary mechanisms in PPO and GRPO introduce fatal bias in long-horizon deep research tasks. GRPO suffers from high variance, which makes the relative baseline noisy. PPO's sparse outcome rewards make it nearly impossible for the critic network to fit an accurate value function. Reinforce works perfectly because it optimizes the policy based on direct cumulative return, bypassing that noisy baseline interference entirely. By stacking these counterintuitive insights, we arrive at the ultimate training recipe, Search R1++. We establish a new, highly stable, and highly efficient baseline. The winning combination is simple: use a fast-thinking template for the prompt to limit unchecked reasoning, F1+ for the reward to prevent answer avoidance, and the classic reinforce algorithm to evaluate direct cumulative return. When we test this, the results are fantastic. Search R1++ substantially outperforms the standard Search R1 architecture, which, remember, relied on slow thinking, EM, and PPO. It maintains robust performance even on compact models, giving us a 3.9% boost on the Qwen 2.5-7B model, and a 4.2% boost on the 3B version. To summarize, here is your RL explainer cheat sheet. The old consensus told us to use slow thinking, F1 scores, and modern algorithms like PPO or GRPO. But the data-backed reality shows we need fast thinking to prevent tag stacking, F1+ to prevent answer avoidance, and reinforce to prevent baseline interference. Ultimately, we need to shift our optimization focus. Future performance gains in deep research will not come from simply throwing richer external tools or newer algorithms at the wall. Real progress requires deliberate, empirical component design. To dive deeper into these findings, be sure to read the full study, How to Train Your Deep Research Agent. Thanks for watching.